Okay, good afternoon, everyone. Let's start. So tomorrow is the university's congregation. So there will be no lecture, no tutorial. Okay, so now let's continue on this microprocessor design. So this microprocessor design example is taken from this book. It is a simple microprocessor without pipelining, but it is a complete microprocessor. It has all the functions of a microprocessor, and there are two microprocessor or CPU architecture. One is called von Neumann architecture. The other is Harvard architecture, and this is of the Harvard architecture. It is so-called because it has separate instruction memory and data memory. The other architecture has a combined single memory block. And in this processor, we're going to implement the 7 instructions. And each instruction is 16-bit long. The data is also 16-bit long. So instruction we are going to implement include add, subtract, load, store, jump. Jump if register 0 equals to 0. And no operation. And this operation code in this as here from 0 to 6. And this is the microarchitecture of the processor. It contains 3 units: register file, ALU, and execution units. We have already discussed this ALU and register. And today we're going to discuss execution unit. But still, let's briefly review what the ALU here has. Say this ALU basically let's look at the input and output ports. It has 2 data input, operand 0, operand 1. Each of them is 16-bit wide, and it has data output called the result, and input the function code, F code, and also carry in and carry out, or the output overflow. That's the carry out. And in this code, we have 5 operations. Actually, only plus or minus. Only first 2 are implemented. The other 3 are not used actually, but you can have you can code this in this way in case you wanted to extend the functions of the ALU. The second block is the register file. Let me briefly review this. Basically, here we only look at the IOs. So it contains 4 registers, and it can be 2 of them. 2 of the 4 registers can be read and write simultaneously. So here you say the so 2 registers you can read or write them, and the registers address read and write control controlled through the input ports here, including this register A read write, register B read write, And the data to write are contained in the input word, register A write, register B write. So basically, this register file has 4 registers there. I can read or write 2 of them simultaneously, and they are control signals. Now, let's have a detailed look at this execution unit, the major control unit here. One module called execution as a long list of input output ports. Let's go through them. The clock input, reset input, 2 wires. And the instruction address. Instruction address should be the output. Let's read the input first. Instruction. The instruction loaded from data memory is a instruction data, 16-bit word. That's an input port. And also input called the register A value. This data, input data, is used for the J0 operation, jump if 0. If this register A input is 0, the jump will take place. That's this operation. That input is used there. Okay. Input. Another input is the overflow, output overflow of the ALU, or is the carry out of the addition or subtraction operation from ALU. So it's the input to the execution unit, as a single wire, and output carry in. It produce carry into the ALU. So it's output port to the execution unit. Then output ports, we have this instruction address. Instruction address to read the next instruction. We need a 16-bit long word. The data address as points to, there's an output pointer, 16-bit pointer pointing to the data memory, the address of data memory. And output operation code is the operation code of ALU, the operation code to control the to select the operation in ALU. And the address. So the address file contains 4 registers. And here the execution points to 2 of them. Call it there's 2 registers called register 0 and register 1. So this is address. This address is simple addressing. We have 4 bits of this register address. Only one of them is high at the time. So this is addressing. So you see the address is NALU N register -120. So the length is N register. It's 4. It's 4 bits, but only one of them is high. And control signal to the register file, including register A read or write, register B read or write, and data read or write. A register here, register A here refers to register 0, same as register 0. Register B refers to register 1. If this register A read write is 0, then it means read. If it's 1, represent the write operation. Now some registers register in execution to store variables, including IR, execution state, instruction address, data address, read write, and those storage in execution unit registers there. So that's the I/O port of this execution unit. Now let's look at the content of this module. Here defines for the convenience, we define some parameters. Say define fetch as 0 as with a value of 0, decode 1, SQ 2, load 3. So this execution is a final state machine. It has 4 states. Fetch instruction from instruction memory, and decode it, then execute the instruction. Then the last one is to read or write data into the data memory, and then it goes back to fetch. So this is 4 states in cycling operation. Now for the instructions, there's 7 instructions given here. The instructions are coded in the MSBs, 4 MSBs. In the first 4 MSB bits, they are representing the operation code, add, subtraction, or so on. Then for the so this is some details or definition of this instruction set. The register zeros address. If it is L subtract, register zeros address is contained from bit 11 to bit 8. Register 1's address is contained in from bit 7 to bit 4 of this instruction. And the bit 3 to 0 is not used for add and subtraction. Now for load and store, this is access to the data memory, external to this processor. Okay. So extra, they have the code of 0 and 1, and load and store I think is 3 and 4, or 2 and 3. It's shown here. So this is the code, opcodes code in the from bit 15 to bit 12. Okay, load and store. So first of all, bits is the code, and then bit 11 to 8 contains the address of the source or destination register. So this load and store is to say to communicate the data between a register and a memory location. So bit 7 to 0 contains the address of the data memory. And jump, the program counters offset. If a jump occurs, then the program counter will jump for an offset. And this offset value is stored from in bit 11 to bit 0. Jump if 0, J0, check the value of the register point in with this address. So bit 11 to 8 contains address of this register. If this register's content is 0, then it will jump by offset given here. given in bit 7 to 0. Otherwise, jump will not occur. Now, for convenience of talking about the position of this instruction, we define this parameters. Op A is bit 15. Op Z is bit 12. A is starting point, Z is end point. Argument 0. A is starting from n-5, which is 11. Argument 0 ending at the bit n-8, which is 8. Argument 1 starting bit is n-9, which is 7 here for n equal to 16. Argument 1, the end bit is 4. So for convenience, operation code it was given in the table before. Now it's defined here. Add is 0, subtraction is 1, and so on. Okay, now the major content of this execution unit. There is an always block. Look at mainly look at the positive edge of clock, but it also look at the reset. If the reset is high, then you reset it. So now look at this. So when this activation list is triggered, then it start this block. First, we look at whether it is reset or not. If reset signal is high, then reset the processor. So the execution state returns to fetch the first state. Register rewrite control are 0. The data rewrite is also set to 0. No operation for the ALU. Instruction address returns to the 0 location. Now, if it is not reset, we start this block. So we look at the execution state, there are 4 states. We look at case state. If the execution state is fetch, we do this. 'Assign the 16-bit input of stored from instruction port to internal register IR, so just to fetch the data and fetch the instruction from the instruction memory and to store in a register in this module. And this is fetch, so no write operation. Set the register A, register B is rewrite to 0. Data and rewrite to 0. And set the next state. Execution state, update the execution state to decode. So next state will be decode, and ALU has no operation. Okay, now if the execution state is decode, then do this from here to here. Here, next state must be SQ. So we set the next state to be SQ. Here, you don't need another variable next state. I just use SQ. You change the value of the S state because it will only update at the rising edge of the clock. So basically, this is the next state. Now decode. Okay. So to decode the instruction, so we have a 16-bit input. It is stored in IR. So we look at the bit 15 to bit 12 of this instruction. If it equals to J0, jump 0. Jump 0 is 5. It's defined earlier. This simple. Then, if it's jump 0, then we set the register 0 address to bit 11 to bit 8 of this instruction, to these bits of the instruction. That's the address of register 0. Now, if the instructions bit 15 to bit 12 equals to jump, then in the decode operation, there's no special operation. If the code is low, then we need to find the address for the source. Should be found for the for this register address, and the address of the data memory is low. Set up the destination. We load data from data memory into the register. So register 1, where as address is found from bit 11 to bit 8 of the instruction word, and data address is 16-bit. So we pad this address with zeros in the MSB. So pad it with zeros because the address is 16-bit long. Then let's store if the bit 15 to 12 equals to store. We do the same thing as the low, except not basically we have the same thing. We find the register 1's address and destination and the data memory's address. If it is add, instruction is add, we need to find the address for register 0 and register 1, as shown here. The address are contained in the instruction bits. If the subtraction, the same to find the register 0 and register 1's value address. Let me see this. All the slides are basically the same as the one poster. I just combine some slides and put the graph, put the existing graph here, figure here, for the convenience of my explanation. Basically, nothing is updated. It's just this: the jump and 0 should be jump 0. All the others are given in the lecture, in the post-lecture notes. Okay, so that's the decode operation. Basically, is find the address for register 0, register 1, and sometimes the data memory is address to decode it. Now, next is the SQ. SQ, we execute the instruction. So do this. Yes. First, set the next state to be load and store, our last one. Now we look at the instructions code. We have this case statement. If the instruction code is add, then we do this. Here, we set basically we set the ALU's the output to ALU operation code to be add, and we increase the instruction address by 1. We increase the address by 1 to prepare for the next instruction. set some input output pins. The carrier in is set to 0. We don't use the carrier in here. And for the add operation, we add the content of register 0 and the content of register 1 together, and the result is going to be stored in register 0. So result will be stored back to register 0. So we set the register 0 read-write control to 1. We are going to write the result back to register 0. Register A is register 0. That's the add operation. Therefore, subtraction is similar to add operation. Nothing special. Well, I add some comments here. If you like, I can post this lecture notes again to the Blackboard. Low. If the instruction is low, we load some data from data memory to a internal register. So the data from memory is to write to register 1 or register. So we set it as register B rewrite this control signal to 1. We're going to write it. Similarly, instruction address is increased by 1 for every case here. And store. Increase the if the to execute the store we set, so ALU is not involved here. No, ALU is also not involved. Only memory is involved. So the data memory, we're going to store some value in internal register into the data memory. So we set the data memory read-write control signal to be 1. We're going to write data from register 1 to data memory. A jump. If it's jump, then the only thing is to update the instruction address for next instruction. It's jump by this offset. Jump 0 is a conditional jump. So it checks the register A value. This is the input port. Input port. It contains the value specified by this register address. So this register address points to a register file. Yeah. Oh, sorry. Let me close this. So this register 0 points to is a pointer. Points to register file, and the content of that register. Content of that register is an input port to this execution module. So that is register A's value. We check if this content is 0 or not. If it is 0, then jump. Otherwise, no jump. Okay, so last execution, execute the instruction. Last one is the load store. This load store is to, if the instruction is a load or a store function, we need to have a clock cycle to complete this access to the data memory. I'm going to set the next state to fetch. But the load and store this state is not necessary if the input is add, subtraction, or jump, but for simplicity, we always go through this last execution state. Then this completes the execution module. Any questions? If no, now here is the lastly we put together the 3 units to form the complete processor. This processor is here, is shown here. So it has, let's check the I/O ports with clock input, reset input, and the instruction value input. Instruction value, instruction data here, input from instruction memory, and data value. And the I/O port address, instruction address, data address. This can be input on or output. And output data rewrite to control real write operation to the data memory. And the register B value output port is 16-bit long. That's this data value. It's from register file to the data memory. You will going to write the data. So we take the content of a register here and pass it to the data memory. So it's this port. And there's some internal wires. Say here, register A and B. It's communication between execution unit and register file. And register A's value, register B's value, rewrite control. So this, you see, the ALU takes is connected to register file. So the 2 operands, and the result is going to write back into register file. Say here, as just register 0 is the input, register 1 is another operand input. The result is going to store back to register 0. Okay, and then put them together and it forms a complete microprocessor. Okay, you see the designing a processor is not that difficult. Only a few slides here, but although it's simple, but still a very complete processor. It has all the necessary function of a processor. Any questions? If no, let's move to next part. Let me close this. Okay, here comes to our last part of the course about testing. This is the outline for this part. So we are go through First, some basic concepts about testability, and introduce important fault models. Next is automated test pattern generation, followed by some design for testability techniques. And lastly is some chip debugging tools introduction. See, let's any questions from the online audience? No. Okay. So testing. So this is about IC design, not really about FPGA. So after an IC is fabricated, it is obviously necessary to go through testing, because not every die on the wafer will work without problems, right, due to process variations and errors. Testing is performed by driving the IC with a stimulus, or called test vector, and comparing the output of the IC with expected results. And the test vector can be the same as the simulation vectors required in the design verification phase. But the test vector should normally be generated specifically for testing purpose. Testing is often done twice, one before packaging, right, on the wafer stage without packaging IC, so that fault-free dies are packaged. The second is after packaging to ensure a fault-free IC. The testing cost can contribute significantly to the total cost. Because this cost cannot be reduced readily with the scale of production. You need to test every IC. So reducing the test cost is an issue that can only be resolved by a better design with testability considered. So what is the term testability mean? Well, testability is to quantify how easy or how difficult a design can be tested. Many approaches exist, but all of them are based on a similar concept. Say we wanted to test a module within a large IC. The IC has primary inputs and primary outputs, so you can send a signal directly to the primary inputs and observe signals at the primary outputs directly. Just say you have a module just deep inside this circuit. You cannot access its input to this module directly, and you cannot observe the output directly. But in order to be able to test this module, we should make sure that input to this module can be easily controllable through this primary input. Somehow the input here can propagate to the input of the module. And the output of the module can be propagated to the primary outputs. Hence, those inputs to the module can each be given a quantity called controllability. How well we can control the input to the module. Likewise, the module's output can be given a quantity called observability. The ability to observe the module's output at the primary output. So the testability of a node in the circuit. It's the product of its controllability and observability. And the product of all the controllability of all the nodes. It's called the total testability of a circuit. Of course, this metric can only be used to evaluate the variance for the same design. The possible cause of a failure of a circuit are numerous, such as an open metal wiring, metal interconnection is broken, or two wires are short circuit due to some manufacturing fault. Incomplete opening of contact holes. A device source or drain node short to the device gate due to misaligned, or basically due to errors in the manufacturing process, or crystalline or direct defects resulting in some anomalous device currents, etc. So we have plenty of physical causes for failure. The possibility is simply too numerous to be addressed. But the alternative is to make use of a fault model, which is how physically faults will express themselves logically. The first fault model is called stuck-at fault model. And this is the most widely adopted fault model among the VLSI test engineering community. It is to assume that physical circuit faults result in stuck at 0 or stuck at 1 error. Say a node here. Say, for example, we have an two input NOR gate. Here, if this PMOS is faulty, its source and drain cannot be turned on, and then the output of this gate will always be 0, and this is named as stuck at the 0. Stuck at the 0 fault. It's always at the 0, no matter what inputs are. Sometimes you can have stuck at 1 fault. This is some simple model. And in this model, you assume that there is only one stuck at the fault in a circuit. There are other fault models here. And we have this multiple fault model. The multiple, it assumes there are multiple stuck at fault in a circuit. This is a straightforward extension of the single stuck at the fault model. Bridging faults. Bridging faults are caused by shorts between two normally unconnected signal lines. So you have two wires, they are accidentally short together. Since the lines involved in this fault have become equal potential, they have the same potential. So all of them have the same logic level. They can vary. They are not stuck to 0 or 1, but they have the same potential, same logic value. So for this kind of file, we need to distinguish between the value one could actually observe on it and the one determined by the source. A third fault model is called AC faults. These faults are some faults are performance related. It causes a device to malfunction at some high clock frequencies. They are not likely to be detected until system level functional testing. The last one I'm introducing here is stuck open fault. So in some logic circuits, we may have opened between a transistor and the supply rail. If we have such kind of open fault, then the circuit, say here, the fault is input dependent. Such fault has the behavior of some flip-flops. Actually, some flip-flop circuit implementation, they apply the floating node concept. And here, if we have an open connection and some node is open, it's the behavior of a sequential circuit. All right, I think that's all for today. Questions? If no, I'll see you next week.